to talk about our second topic of derivatives today, and you won't quite see the actual definition of derivatives today, but we're getting really close. So we will still use limits, but more infrequently than before. So here we have two formulas for the average rate of change. Average rate of change you could find way back when you first learned slope, because the slope formula you see is an average rate of change right there. The difference quotient formula would have popped up in pre-calculus on occasion. We're going to use both of these fairly often. Slope formula, of course, you first learned as y2 minus y1 over x2 minus x1, and it's just written differently now. It's not used any differently. Just notation is slightly different. Okay, so we're going to use those ideas of average rate of change to eventually find instantaneous rate of change. And that problem is actually what caused calculus to be invented by these two gentlemen. Newton and Leibniz are the two men credited with the invention of calculus. So the story behind these two and who actually invented it has a lot of drama in it. If you ever want to know, I'd happily tell you, because I took a history of math class to be a teacher, and I like to share that information, but don't want to waste time on the video. So if you want to know more about the drama between those two, ask me in class. But those two invented calculus. So instantaneous rate of change is more what we're wanting to find in calculus. We knew before we could find average rates of change, but the instantaneous rates of change are definitely what we want to be working towards. So you'll see that the slope formula and difference quotients that we had on the very first screen are now here, but with an added limit notation in front of them. So if we take the limit as our 2 points in the slope formula get closer and closer together, we'll have an instantaneous rate of change, and difference quotient, same thing. If h is representing the distance between 2 points, we're going to let that distance go to 0 and have our instantaneous rate that way. Pro tip there, you will each probably develop one of these, a strong favoring of one over the other, but it is super important that you do learn how to use both of them, because we use both of them in calculus, and it kind of just depends on the information you're given. So get used to both of them, use both of them. Of course, use your favorite one anytime you can, but keep the other one in the back of your mind too. Okay, we're going to take the same problem, the f of x equals x to the fourth minus 5x, and find instantaneous rate of change at the point x equals 2 using both formulas, just so you can see how they are slightly different. So the first one we're going to do is using the slope formula. So slope formula, I think, works best when we actually have this x value. That is where we type in f of a. So that tells us a is 2. And since we're going to need that f of a value in our formula right up top, we're going to calculate that right now. 2 to the fourth, 16 minus 10. So f of 2 is going to equal 6 when our a is 2. So we're going to start limit x approaches 2. So x will always stay x in this formula. A is what becomes 2. F of x is just our function definition, so x to the fourth minus 5x, and f of 2 was 6, so I'm going to subtract 6 over x minus 2. Now we have a limit that we talked about how to evaluate before, and of course we try direct substitution. Direct substitution doesn't work, we fail miserably. So this means maybe I try synthetic division. 2 goes out in the little box. X to the fourth has a coefficient of 1. X to the third, x squared have 0 coefficients. Then we have a negative 5 and a negative 6. And if you remember synthetic division, you drop the 1 down, multiply, add, multiply, add, multiply, add, multiply, add. And Now we know that that numerator here factors into x minus 2, and this cubic polynomial that we found through synthetic division. Okay, never could I have factored that without synthetic division, so I put this example in on purpose to remind you of synthetic division. And now I'm going to do my limit as x approaches 2 of x cubed plus 2x squared plus 4x plus 3, because I eliminated that problem of x minus 2 in the denominator. So 2 cubed, 8, 4 times 2 is 8, another 8, and 3. This limit appears to be 27. And that's how it works. So the instantaneous rate of change at x equals 2 of our function is 27. We don't know what units we were looking at, but it's 27 somethings. Okay, so not too bad, not too bad. We're going to keep in mind that 27 that we just had, we should have 27 at the end of this problem too. It is the same f of x, it is the same x equals 2. We're just going to use the other formula. And this one is really nice when we don't necessarily know all of the variables, so we will end up using the difference quotient a lot more towards the middle of this chapter. So let's see what this looks like. Still same formula there, so we fill everything out. We're going to have the limit as h approaches 0 of, to find f of x plus h, you take x plus h and plug it into the f function. So we're going to have x plus h to the 4th minus 5 times the x plus h. And then we're going to subtract all of f of x. So f of x is x to the 4th minus 5x over h. Okay. We could have also, if we wanted to, because we know x is 2, we could change all of these into 2's. And maybe that would be a good idea to do, so you actually see how to do that. So I'm going to change all of my x's to 2's. So 2 plus h, 2 plus h, 2 to the 4th, like that. 5. Okay, now 2 to the 4th power. If you remember Pascal's triangle, 2 to the 4th power, or 2 plus h to the 4th power, isn't too bad. So if you don't remember it, we'll draw just a little piece of it over here. And this is the row we would need, our coefficients of 1, 4, 6, 4, 1, to expand out that 2 plus h to the 4th power, the binomial theorem. So limit as h approaches 0. I'm going to take up a little room here. So the first thing is the first 2 gets raised to the 4th power. Then we would have our next coefficient of 4 times 2 to the 3rd times h. Then we would have a coefficient of 6 times 2 squared times h squared. So this is just expanding that first binomial. Then we have the coefficient of 4 times 2 to the 1st, h cubed, and our last one, h to the 4th. All right, that's going to be in my way, so I'm going to get rid of it. Now we're going to subtract 5 times 2 plus h. So that's a minus 10 minus 5h. And if you remember our f of 2 from before, it was 6. Back on this one, we had f of 2 equals 6. So I'm just going to write minus 6 there, all over h. Now we simplify. We have a lot of crazy business going on in there. Pretty gigantic fraction. So 2 to the 4th power, 16, This is 32h, 24h squared, 8h cubed, h to the fourth, and we still have minus 10 minus 5h minus 6. Okay, now start combining the like terms and canceling things out. Anything that we can think of to do over there, we're going to want to do that. So I see that we have a positive 16 and a negative 10 and a negative 6 gets everything to cancel out. And there's also some like terms of a 32h minus 5. So let's combine those and factor out the h at the same time, because notice everything has an h in it. So I'm going to do two things at once here. Factor out an h, combine that 32 and negative 5 to get 27. Okay, this allows me, of course, to cancel out that problem that we were having with the h in the denominator, division by 0. Now it's gone. We can try direct substitution again, and anything with an h in it is going to go to 0. So this limit, bet you weren't expecting 27, huh? There's how we get our 27 using the difference quotient. So one of them seems a little more algebra based, and one of them is a little more numerical based, but both totally doable. Like I said, this one, the difference quotient method, is probably going to be more common as we go through calculus, but get to know them both and use them both. Let me know if you have any questions or want to hear